Welcome to the Explainer. Today we're tackling something that sounds, well, impossible, predicting random events. But you'd be absolutely amazed at what we can figure out when we have the right statistical tools.
Okay, let's jump right in with a question we've all asked ourselves. You're sitting there watching a drive-thru or maybe the line at a ticket counter, and you're just wondering, what's going to happen next? Is it all just random chaos?
Well, not quite. It turns out what looks like total randomness often has a hidden pattern. And yeah, you guessed it, statistics gives us the exact tools we need to uncover it.
So the first tool we're going to grab from our toolbox is called the Poisson Distribution. This thing is perfect for counting how many times an event pops up over a specific stretch of time or space.
And you see this everywhere. Think about the number of emails you get in an hour, or the number of typos on a page, or even the number of shooting stars you might see in a given night. All of that's Poisson territory.
Now for this to work, two things have to be true. First, the chance of something happening in 1 minute is the same as the chance of it happening in any other minute. Makes sense. But second, and this is the big one, each event is totally independent. One car pulling up has absolutely no effect on whether another car will pull up a second later.
All right, let's stop talking theory and put this to the test with our bank drive-thru.
So first things first, we need an average. The bank's been keeping track, and they know that on average, 10 cars show up every 15 minutes. In the world of stats, we call this our expected value, or mu. That number, 10, is our starting block.
But here's the catch, right? An average is just an average. Life isn't always average. So what are the odds that in the next 15 minutes, exactly 5 cars show up? Not 4, not 6, but precisely 5.
We run the numbers through the Poisson formula, and this is what we get. There's a 3.78% chance of exactly 5 cars arriving. It might not seem like a high probability, but it's a real concrete number for something that feels totally random. Pretty cool, right?
And you know, this isn't just a fun math puzzle. This has serious real-world applications. Bell Labs, the famous innovation hub, used this exact kind of math to figure out how many telephone calls they could expect, which literally helped them build the phone networks we used for decades.
Okay, but what happens when that golden rule of independence gets broken? What if one event does change what happens next? Well, that changes the whole game.
Just look at the difference here. With the bank, the number of cars on the road is huge, practically infinite. One car showing up doesn't change anything. But now imagine you're picking fuses out of a small, limited box. Every single fuse you take out changes the odds for the very next one you pick. They're connected.
For this new kind of problem where you're picking from a small batch and not putting things back, we need a different tool. And that tool is the hypergeometric distribution.
The key phrases here are without replacement and finite population. It means the trials are dependent. Every draw changes the probability of what comes next.
So let's see how this works with a classic quality control problem. I think this will really make the difference click.
Okay, so here's the setup. You've got a box with 12 fuses in it. You know for a fact that 5 of them are bad. A quality inspector walks up and randomly grabs 3 of them to test.
So, here's the big question. What are the chances that in that handful of 3 fuses, the inspector finds exactly 1 of the bad ones? And remember, once a fuse is picked, it stays out.
Now, before we even touch a formula, let's just think about the logic. It's all about combinations. We just need to figure out how many ways there are to get the result we want, 1 bad fuse and 2 good ones, and then divide that by the total number of ways you could possibly pick any 3 fuses from that box.
And when you do the math, you get this, a 47.73% chance. Wow, that's actually a really high probability. It's almost a coin flip that the inspector will find exactly 1 bad fuse in that small sample.
Okay, so we have these 2 really powerful tools, Poisson and hypergeometric. The million-dollar question is, how do you know which one to use when? Think of this as your cheat sheet. If you're dealing with events that are independent and coming from a huge pool, like our cars, you use Poisson. You're asking, how many in this time frame? But if your events are dependent and you're picking from a small, limited batch, like our fuses, you go with hypergeometric. You're asking, how many successes in this sample?
And honestly, if you walk away with just one thing today, let it be this. It all comes down to independence. That's it. Are you counting separate arrivals, or are you picking from a box where each pick changes the game? Answer that, and you know exactly which tool to use.
And that's our look at these 2 incredible ways to predict the unpredictable. So I'll leave you with a question to chew on. What about calculating your odds in a card game, or estimating the number of fish in a lake? Now that you know the difference,
which tool would you reach for?